Now, in this lecture, we find out the length of line segment X using two different methods. In the drawing, we have a semicircle that is inside a quarter circle. We know that side AO equals to 6 units, and also side AC or tangent AC is tangent to the semicircle at this point. And we want to find out the length of side AC that is equal to X. So we'll start with the first method, and we'll define the point of tangency of tangent AC with this semicircle as point D. And we'll define the center of this semicircle as point P. Actually, because of the fact that AOB is a quarter circle, then this angle AOB must be equal to 90 degrees, and AO is the radius of the quarter circle that is equal to 6 units. Why? Because line segment AO starts from the center of the quarter circle, that is to say from point O, and ends at point A, that is a point on the quarter circle itself. And this is exactly the definition of a radius. And exactly for the same reason, OB, it is also the radius of the quarter circle. That is to say, it is also will be equal to 6 units. I repeat again, because of the fact that line segment OB starts from the center of the quarter circle, that is to say from point O, and ends at point B, it means that it is the radius of the quarter circle. But OB, line segment OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. Okay? So we know that the diameter of this semicircle equals to 6 units. And the diameter is twice as large as the radius. So if the diameter of the quarter circle is 6 units, it means that the radius of this semicircle will be equal to half of it. That is to say, the radius of this semicircle will be equal to 6 over 2, that is 3 units. So OP equals to 3 units, and PB equals to 3 units. OP and PB are the radii of this semicircle, because of the fact that they start from the center of the semicircle, that is to say from point P, and end on the semicircle itself. At point B, that is a point on the semicircle itself, and point O, that is a point on the semicircle itself, and this is exactly the definition of a radius. Therefore, both of them are the eye of the semicircle, that is to say they are equal to 4 units. In the next step, we will join together points P and D by a straight line. PD is also the radius of the semicircle, that is to say it is equal to 3 units. Why? Because it starts from the center of the semicircle, that is to say from point P, and ends at point D, that is a point on the semicircle itself. And this is exactly the definition of a radius. Okay? In the next step, we join together points A and P by a straight line. And I will present to you a new wall. This is actually wall number 1. According to wall number 1, the lengths of two tangents from a common external point to a circle are equal. I will read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we also have this point P is an external point in relation to this circle. Why point P is an external point of this circle? Because point P is not located inside this circle, nor on this circle, but it is located outside of this circle. Therefore, point P is defined as an external point of this circle. So if the external point P, we will draw two tangents to this circle. Then here, the first tangent will be this tangent, we will define the point of tangency of the first tangent with this circle as point A. Again, point A is the point of tangency of this tangent with this circle. Okay, and then we will draw a second tangent to this circle. And we define the point of tangency of the second tangent with this circle as point B. And according to rule number 1, the lengths of two tangents, that is to say the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the lengths of two tangents, that is to say PA and PB, from a common external point, that is to say from point P that is a common external point, to a circle, 2 points A and B are equal. That is to say PA is equal to PB according to rule number 1. Okay, so whenever you draw two tangents from a common external point of this circle to that circle itself, to point A and B, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. Okay, so we actually can implement rule number one in our drawing. Why? Because in our drawing we have the common external point, point A. Point A is the common external point in relation to the semicircle, because it is located outside of the semicircle, and from the common external point, point A, we have two tangents to this semicircle. The first tangent is tangent AO. The point of tendency of tangent AO with this circle is point O. And the second tangent to this semicircle is tangent AD. The point of tendency on the second tangent with this semicircle is at point D. And according to rule number one, the lengths of those two tangents are equal to each other. That is to say, AO equals to AD. So I write it down. According to rule number one, the lengths of those two tangents are equal to each other. That is to say, AO equals to AD, according to rule number one. The lengths of those two tangents are equal to each other. That is to say, AO equals to AD, according to rule number one. But here it is given us in the question that AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation, 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Okay, AD is also equals to 6 units. So here AD equals to 6 units, so we can write down here that AD equals to 6 units. In the next step, we will prove that those two right triangles can point to each other. That is to say, triangle AOP can point to triangle APD, and they can point to each other according to side rule. So I'll write it down. We prove the triangle AOP, this right triangle, this right mid triangle, triangle AOP, triangle AOP congruent, this is the sign of congruent, to triangle ADP. ADP this main right triangle, triangle ADP. So why those two triangles can go into each other? They actually can go into each other according to side rule. Okay, so why they can relate to each other? Because of the fact that side AO equals to side AD equals to 6 units, according to rule number 1. AO equals to AD equals to 6 units, according to rule number 1. We also have side AP, that is a common side, it belongs to both triangles, so AP equals to itself. AP equals to AP is a common side that belongs to both triangles. And finally, side OP equals to side PD equals to 3 units. It is the radius of the semicircle. OP equals to PD equals to 3 units is the radius of the semicircle. So we actually found out that all the sides of the green triangle AOP can relate to all the sides of the green triangle APD, therefore those two triangles can relate to each other according to side rule. And from the fact that those two green triangles can relate to each other, we conclude hence, we conclude from it those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can relate to each other, therefore those two corresponding angles will be equal to each other. So that is to say, angle OAP, this angle is equals to angle PAD, this angle repeat again, according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define angle OAP as theta, here angle OAP equals to theta according to our definition, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. Okay, here angle PAD is also equals to theta. In the next step, we will join points O and C together by a straight line. So related here, triangle AOC. We will focus on the right triangle, triangle AOP. In the right triangle, triangle AOP, this right green triangle, we know that triangle theta equals to OP over AO. repeat again. In the right triangle, triangle AOP, triangle theta equals to OP over AO. Here, OP equals to 3 units, it is the radius of the semicircle, and AO equals to 6 units according to what is given us in the question. Therefore, we found out that triangle theta equals to 3 over 6. We divide this equation, this side of the equation by 3, and we get that triangle theta equals to 1 over 2. So in conclusion, we found out that triangle theta equals to 1 over 2, that is 1 half. Triangle theta equals to 1 half. Triangle theta equals to 1 half. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle AOC. So, what is the law of cosines? Actually, I already mentioned the law of cosines in the previous lecture, so I will repeat the explanation shortly. So actually, the law of cosines is true in any triangle. So actually, if we have triangle ABC, that could be any triangle, this is triangle ABC. And we know that side AB of this triangle, triangle ABC equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. This equation is true in any triangle. I repeat again, in this triangle, triangle ABC, C squared equals to A squared plus B squared minus 2 times AB times cosine theta. Okay, so we will implement the law of cosines in our triangle, triangle AOC. So I will copy triangle AOC in this page, and we will implement the law of cosines in this triangle AOC. So Side AO equals to 6 units according to what is given as the question. Here OC, the line segment OC starts from the center of the quarter circle, that is to say from point O, and ends at point C, that is the point on the quarter circle itself, and this is exactly the definition of a radius. That is to say OC is the radius of the quarter circle, that is equal to 6 units. So OC equals to 6 units, and AC is the line segment that we are looking for, that is to say AC equals to 6 according to what is given as the question. And angle OAC equals to theta plus theta, that is 2 theta. So actually this is triangle AOC. Triangle AOC that I copied from the original drawing. Side AO equals to 6 units, side OC equals to 6 units, and AC is the line segment that we are looking for, that is equal to X, and angle OAC equals to 2 theta. So we will implement the law of cosines in this triangle, triangle AOC. This will be equation number 1. So here C squared, it is actually OC squared. It is equal to A squared is AO squared plus B squared, that is actually AC squared, that is equal to X squared minus 2 times AO times AC times cosine 2 theta. Okay? So here OC squared is 6 squared, that is 36. And it is equal to AO squared. AO squared is 6 squared, that is also 36. Plus AC squared. AC equals to X. This is the line segment that we are looking for. So AC squared will be equal to X squared minus 2 times AO is 6 times AC is X times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. And what is left after we cancel 36 from equation number 1? In this side of the equation we have 0. That is equal to X squared minus 2 times 6 is minus 12. So this expression equals to minus 12 X times cosine 2 theta. Here we will add 12x cosine 2 theta to this equation, equation number 1. And we will get that according to equation number 1, 12x cosine 2 theta equals to x squared. Here we will divide this equation, equation number 1, by x. You can see from the drawing that x is the length of side AC. This is the variable that we are looking for. So x is a length, it must be a positive number. It can never be equal to 0. And that is the reason that it is allowable to divide by x, because of the fact that x can never be equal to 0. We can divide this equation number 1, by x. Okay? So we divided the equation number 1 by x, and here we get that according to equation number 1, 12 times cosine 2 theta equals to x squared over x is x. So 12 times cosine 2 theta equals to x according to equation number 1. So the only thing that is left here, okay, we have to find out the value of cosine 2 theta, and in this way we'll find out the value of line segment x, that is the line segment that we are looking for. Okay, so the only thing that is left to do is to find out the value of cosine 2 theta. Actually, we have trigonometric identity for cosine 2 theta. Here cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta, and we have already found out that tangent theta equals to 1/2. So I can write here that tangent theta equals to 1/2, according to what we have already found out. Now we can substitute tangent theta in this trigonometric identity by 1/2. We'll do it now, and we get that according to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1/2. Therefore, tangent square theta will be equal to 1/2 squared. Okay? So in the numerator we have 1 minus 1/2 squared over, in the denominator we have 1 plus tangent square theta, and tangent square theta equals to 1/2 squared. One half squared equals to 1/4, so I write it down, cosine 2 theta equals to 1 minus 1/2 squared is 1/4 over 1 plus 1/2 squared, that is 1/4. So here 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. So we have here, we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And in conclusion, we found out that cosine 2 theta equals to 3/5. Cosine 2 theta equals to 3/5. or to 3/5. Now we can substitute cosine 2 theta in this equation number 1, by 3/5. Here we have equation number 1 that says that 12 times cosine 2 theta equals to 3/5. Because yeah, actually equation number 1 states that cosine 2 theta equals to x. Cosine 2 theta equals to x. Now we can substitute cosine 2 theta in this equation number 1, by 3/5. We'll do it now, and we get that according to equation number 1, 12 times cosine 2 theta is 3/5, and it is equal to x. X is the variable that we are looking for. So here, according to equation number 1, x equals to 12 times 3 is 36 over 5. So 36 over 5 is 7.2 units. So we actually found out that x, the variable that we are looking for, the line segment that we are looking for, it is equal to 7.2 units. Okay. Now x it is actually also equals to AC. X equals to AC, it is equals to 7.2 units. And that is the answer to the question. AC equals to X equals to 7.2 units. So we finished with the first method. In the next step I will present to you how to find out the length of line segment X that is equal to AC according to the second method. In the second method, we will use in all the fields that we have already found out in the first method. In the center of the semicircle is point P. The point of tendency of tangent AC with this semicircle is point D. We have already known that AO is the radius of the quarter circle that is equal to 6 units. OP is the radius of the semicircle that is equal to 3 units. PB is also the radius of the semicircle that is equal to 3 units. Here PD is also the radius of the semicircle that is equal to 3 units. Here we have we join points A and P by a straight line, and this angle equals to angle over B equals to 90 degrees. We have already found out that triangle AOP, this right triangle, congruent to triangle APD, this right triangle, according to side rule. And from the fact that those two triangles can go into each other, we concluded that angle OAP equals to angle PAD. Okay, angle OAP is equal to angle PAD, this angle. And if angle OAP equals to theta, then from this equation we derive that angle PAD is also equals to theta. We have already done these things in the first method, so I will not repeat on it. So if angle OAP equals to theta, then angle PAD must be also equal to theta because of the fact that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Okay? So here, in the next step, we will extend line segment AC and line segment OB by a straight line until they intersect with each other. And we define the intersection point of the extended line segment AC and the extended line segment OB as point E. Point E is the intersection point of the extended line segment AC and the extended line segment OB. So we actually created here the right triangle, triangle AOE. Again, triangle AOE is the right triangle. And line segment AP is angle bisector because of the fact that line segment AP bisects angle OAE into two halves. The first half is theta and the second half is also equal to theta. So I copy the right triangle AOP in a new page and we implement the angle bisector theorem in this triangle, triangle AOE, but before that I will explain to you what is angle bisector theorem. Angle bisector theorem is true in any triangle, so if we have triangle ABC, that could be any triangle. This is triangle ABC. So this is the angle bisector theorem. Okay, the angle bisector theorem. This is triangle ABC that could be any triangle. And we have line segment AD. Here, this line segment AD is angle bisector. Why? Because it bisects angle BAC to two halves. The first half equals to theta and the second half also equals to theta. So in triangle ABC we have the angle bisector AD. And according to angle bisector theorem, the angle bisector in a triangle, the angle bisector, that is to say in this case is AD, the angle bisector that is AD, line segment AD, divides the side that it is, divides the side that it is. In this case, angle bisector AD is side BC. Okay, so I can write down that in brackets that we relate to side BC, of course, because angle bisector AD is side BC. In a ratio so actually in a ratio angle bisector AD is side BC at point D, and it divides it into two parts, side BD and side DC. And the ratio between those two parts is equal to BD over DC. And that ratio, it is equal in a ratio that is equal to the ratio of the angle's legs. The ratio of the angle's legs. The angle's legs are AB and AC. Again, the angle's legs, the angle that has been bisected into two halves is angle BAC, and the angle's legs is side BA and side BC. And the ratio between those two legs is BA over BC. So the ratio between the angle's legs is equal to the ratio that angle bisector AD divides side BC, that is to say, it is BD over DC, or in other words, here BA over BC over DC, BA AB over AC. Again, the ratio between the angle's legs is AB over AC. The ratio between the angle's legs is AB over AC. And this ratio is equal to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. BD over DC. So write it again here, that AB over AC equals to BD over DC. Okay? This is the equation for the angle bisector theorem. It means that the angle bisector AD divides the side that is actually BC, in a ratio that is equal to BD over DC. And that ratio is also equal to the ratio between the angle's legs. And the ratio between the angle legs is AB over AC. So the ratio between the angle legs, that is AB over AC, equals to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. So in conclusion, AB over AC equals to BD over DC. Okay, the ratio between the legs of the angle that has been bisected, that is AB over AC, and that ratio equals to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. So in conclusion, we found out that according to angle bisector theorem, in triangle ABC, AB over AC equals to BD, AB over AC equals to BD over DC. That is angle bisector theorem, and we will implement. So maybe I will repeat on angle bisector theorem again. The angle bisector, that is to say, in this drawing, the angle bisector is line segment AD, divides the side that it eats. Angle bisector AD eats side BC of triangle ABC, and it divides it into two parts, part BD and part DC. And the ratio between those two parts is BD over DC. And that ratio is equal to the ratio between the angle's legs. The legs of the angle that has been bisected. First of all, we are talking on angle BAC. And the legs of angle BAC are BA and AC. And the ratio between the legs of angle BAC is BA over AC, or AB over AC. So the ratio between the angle's legs, that is AB over AC, equals to the ratio that angle bisector AD divides side BC. And that ratio equals to BD over DC. So in conclusion, we found out that AB over AC equals to BD over DC in triangle ABC. So we can implement the angle bisector theorem in our drawing, or in triangle AOC, because we have AP, that is angle bisector of triangle AOE. So I will copy the right triangle AOE in a new page, and we will implement the angle bisector theorem in this triangle AOE. Okay, so this is triangle AOE, the right triangle. So this is the right triangle AOE that I copied from the original drawing. So we will implement the angle bisector theorem on the right triangle AOE, because here AP is the angle bisector of this triangle AOP. Why? Because line segment AP bisects angle OAE into two halves, if each half equals to theta. Therefore, we can implement the angle bisector theorem in this triangle AOE. So according to angle bisector theorem, we will get that AO over AE that is actually the ratio between the legs of the angle that has been bisected is equal to the ratio that angle bisector AP divides side OE. And the ratio that angle bisector AP divides side OE is OP over PE. Okay? This will be question number 1. So here, according to question number 1, AO equals to 6 units. AO equals to 6 units over AE equals to OP. OP is the radius of the semicircle, that is to say it is equal to 3 units over PE. So here we'll divide this equation number 1 by 3, and we will multiply it by PE, and we'll get that according to equation number 1, 6 over 3 equals to AE over PE. Six over 3 is 2, so 2 equals to AE over PE. Here we will multiply equation number 1 by PE, and we'll get that according to equation number 1, 2 times PE equals to AE. So AE is twice as large as PE, or AE is twice as long as PE. So if we define PE as A, so here PE equals to A, here PE equals to A, so PE equals to A according to our definition. So from equation number 1, we will get that AE equals to 2 times PE, and PE is A, so AE equals to 2A. AE equals to 2A. So we can write here that AE equals to 2A. Line segment AE equals to 2A, while line segment PE equals to A according to our definition. So we will continue to focus on the right triangle AOE. I'll copy the right triangle in a new page. I will copy the right triangle AOE in a new page, and we will implement the Pythagoras theorem on this right triangle AOE. As you can see here, OE equals to 3 plus A. Here you can see also that OE equals to 3 plus A. So write it down. several dimensions. Here OE equals to 3 plus A. So we can write here that OE equals to 3 plus A. And we've already found out that AE equals to 2A. The hypotenuse AE equals to 2A. So in the right triangle AOE, by PT is the abbreviation for Pythagoras theorem, we will get that this will be question number 2. The square of the hypotenuse is AE squared. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. This equals to AO squared plus OE squared. Okay. So here AE equals to 2A, so A squared is 2A squared, and it is equal to AO squared. AO equals to 6 units, therefore AO squared, it will be equal to 6 squared. That is actually 36 plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared. So in conclusion, we found out that according to the Pythagoras theorem here, 2A squared equals to 36 plus 3 plus A squared. We will open the brackets on both sides of this equation number 2. And we'll get that according to equation number 2, A squared equals to 4A squared, and it is equal to 36 plus 3 plus A squared here 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 2 times AB is plus 6A. So actually 4A squared, according to equation number 2, 4A squared equals to 36 plus 9 is 45, plus A squared plus 6A. Here we subtract A squared from this equation number 2, and we get that according to equation number 2, according to equation number 2, 3A squared minus 4A squared minus A squared is 3A squared, and it is equal to 45 plus 6A. So here we divide this equation number 2 by 3, and we get that according to equation number 2, A squared over 3 over square over 3 is a squared, equals to 45 over 3 is 15, plus 6a over 3 is 2a. Here we subtract 15 and also 2a from this equation, equation number 2, and we get that according to equation number 2, a squared minus 2a minus 15 equals to 0. So here we have a quadratic equation. The coefficient a is equals to 1 in this quadratic equation. The coefficient b in this quadratic equation equals to minus 2. And the coefficient c in this quadratic equation equals to minus 15. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable that we are looking for is a, so x equals to a. So we put the data inside the formula for x and we find out the value of the values of a because x equals to a. So we found out here that a equals to minus b, b equals to minus 2, so minus b is minus minus 2, that is plus 2, plus minus square root of b squared, b equals to minus 2, so b squared is minus 2 squared, that is 4, minus 4 times a is 1, times c is minus 15, over 2a. A is 1, so 2 times 1 is 2. So here, a equals to 2 plus minus square root of minus 15 times minus 4 is plus 60, and 60 plus 4 is 64. So inside the root we left only with 64 over 2. So we actually found out that a equals to 2 plus minus square root of 64 is 8 over 2. So here we have two solutions that are possible for a. The first solution is a1, that is equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a1 equals to minus 3. If a is the length of side PE, again a is the length of line segment PE, so a is a length, and as a length it must be a positive number. Therefore a cannot be equal to a negative number, so we will cancel this solution and we left only with the second solution, a2 that is equal to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out actually that a equals to 5, or a2 or 8 is the same, equals to 5. So here we can write down that a equals to 5. and 2A is 2 times 5, that is 10. Actually, AE, line segment AE equals to 10 units, and line segment PE equals to 5 units. And what is the length? What is the length of line segment BE? The length of line segment BE for the drawing, it is very easy to see that the length of line segment BE equals to PB, PE is equals to PE minus PB. PE minus PB equals to BE. Again, PE minus PB equals to BE. Again, PB equals to PE minus PB. That is to say, BE equals to PE, that is 5 units, minus PB. PB is the radius of the semicircle, that is equal to 3 units, so PB is 3. So in conclusion, we found out that B equals to 5 minus 3, that is 2. BE equals to 2 units. Can I tell that BE equals to 2 units? And what is the length of line segment CE? The length of line segment CE for the drawing, it is very easy to see that the length of line segment CE, this line segment, it is equal to AE minus AC. AE minus AC. Again, CE equals to AE minus AC. AE equals to 10 units. And AC equals to X, this is the line segment that we are looking for. So, in conclusion, we found out that C equals to AE minus AC, A equals to 10, AC equals to X. So in conclusion, we found out that CE equals to 10 minus X. C equals to 10 minus X. Here, CE equals to 10 minus X. In the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend line segment BO by a straight line until it touches the circle So the extended line segment BO touches the circle at this point. We'll define the touching point of the extended line segment BO in the circle is point M. Again, point M is the touching point of the extended line segment BO in this circle. So what is the length of line segment MO? The length of line segment MO is the radius of the circle, that is also the radius of the quarter circle. Why? Because line segment MO starts from the center of the circle, that is also the center of the quarter circle, and ends at point M, that is a point on the circle itself. And this is exactly the definition of a radius. That is to say, MO is the radius of the circle, that is also the radius of the quarter circle, that is equal to 6 units. In conclusion, MO equals to 6 units. In the next step, I will present to you a new rule that is actually rule number 3. According to rule number 3, if we have this circle, rule number 3, and rule number 3 says that if two chords intersect with each other outside the circle, that is to say, it is externally, at point P, then the following equation is true. So I read rule number 3 again. According to rule number 3, if two chords intersect with each other outside the circle, that is to say, externally, at point P, then the following equation is true. So here we have point P is the external point of this circle. Point P is the intersection point of the two chords. Okay, so here we have the first chord is chord A, B, and the second chord is chord C, D. I repeat again, chord A, B, this chord intersects with chord CD, this chord, at point P. Point P is the intersection point. Intersection point. Point P is the intersection point. Of the two chords, that is to say chord AB and chord CD. So those two chords intersect with each other at this point, point P. Then the following equation is true. The equation is PA times PB is equals to PC times PD. Okay, PA times PB equals to PC times PD. I repeat again, if the two chords, chord AB and chord CD, intersect with each other at point P, that is a point that is outside the circle, then the following equation is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. Okay? So here we can implement rule number 3 in our drawing. In our drawing, we have two chords, chord OB, this chord MB, chord MB, this chord called MB intersects with chord AC. This is called AC. At point E. Point E is the intersection point of chord MB with chord AC. I repeat again, in our drawing we have chord MB that intersects with chord AC at point E. Therefore, and point E is an external point. The intersection point is outside the circle. If the intersection point is outside the circle, therefore we can implement rule number 3 in our drawing. Therefore, according to rule number 3, we will get that EC times EA equals to EB times EM. I repeat again, because of the fact that chord MB intersects with chord AC at point E is the intersection point of those two chords that is outside the circle, point E is located outside the circle, then we can implement rule number 3 here. And according to rule number 3, we get that EC times EA equals to EB times EM. Okay? This is according to rule number 3, of course. Here, EC equals to 10 minus x, CE equals to 10 minus 6, C is EC, that is equals to 10 minus x. EA is AE, that is 2A, that is 10 units. EA equals to AE, that is 10 units. So here EC equals to 10 minus x and EA equals to 10 units, and it is equals to EB or BE equals to 2 units. Times EM. Here, EM or ME equals to 6 plus 3 plus 3, that is 12, plus 2, that is 14. So in conclusion, we found out that here it is actually MB. Okay, it is MB. So write it down, BM. So BM is 6 plus, no, it is BE. But BE is 2 units, and here EM is actually EM, and EM equals to 14 units. EM equals to 14 units. So in conclusion, we found out that 10 minus x times 10 equals to 2 times 14. 2 times 14 is 28, and 28 equals to 10 times 10 minus x. Here we'll divide this equation by 10, and we'll get that 10 minus x equals to 28 over 10 is 2.8. Here we will add x to this equation, and we'll subtract 2.8, and we'll get that x equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So in conclusion, we found out that x equals to 7.2 units. Okay, x equals to 7.2 units. And that is the answer to the question. Here, x, that is actually also equals to AC, equals to 7.2 units. So in both methods, we found out that the length of line segment x, that is equal to AC, it is equal to 7.2 units. So in the next step, I will summarize the lecture. We'll start with the first method. So, I'll repeat on the question. We have here a semicircle that is inside a quarter circle. We know that AO equals to 6 units, and we want to find out the length of line segment AC that is equal to x. So we define the center of the semicircle as point P. We defined the point of tendency of tangent AC with this semicircle as point D. And here, line segment AO is the radius of the quarter circle because of the fact that it starts from point O, that is the center of the quarter circle, and then at point A, that is the point of the quarter circle itself, and this is exactly the definition of a radius. That is to say, AO is the radius of the quarter circle that is equal to 6 units. For the same reason, exactly, OB, it is also the radius of the quarter circle, that is to say, it is equal to 6 units. Okay, and this angle AOB equals to 90 degrees because we are talking here on a quarter circle, and in a quarter circle, this point is always the center of the quarter circle, and again AOB equals to 90 degrees. Okay, then we join points. So OP is the radius of the semicircle, that is half of the radius of the quarter circle. The radius of the quarter circle, that is OB, is actually the diameter of the semicircle, and the diameter of any circle or semicircle is half of the size of the diameter. So the radius is half of the size of the diameter. So the diameter of the quarter circle is 6 units, and the radius is half of it. That is to say, the radius is 6 over 2, that is 3 units. So here OP equals to PB equals to PD. All those line segments are defined as the radii of the semicircle, that is to say, they are equal to 3 units. Then we join points A and P together by a straight line, and then I presented to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So if we have this circle and point P that is an external point in relation to this circle, and from point P we draw two tangents to this circle, tangent PA and tangent PB, then according to rule number 1, the lengths of those two tangents will be equal to each other. That is to say, in this case, PA will be equal to PB. So whenever you draw two tangents to a circle from a common external point to that circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. So we can actually implement rule number 1 in our drawing, because we have here in our drawing the external point, point A. Point A is an external point in relation to the semicircle. And from the external point, point A, we have tangent AO, that is tangent to the semicircle, is point O. Point O is the point of tendency. And tangent AD, that is tangent to this semicircle, is point D. Point D is the point of tendency. So from the external point, point A, we have two tangents to the semicircle, tangent AO, tangent AD. Therefore, according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, AO equals to AD according to rule number 1. Okay, here AO equals to AD according to rule number 1. But it is given us the equation that AO equals to 6 units. So here AO equals to 6 units, and so from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Here AD equals to 6 units. Then we proved that the two green right triangles can go into each other according to side rule. Again, triangle AOP can go into triangle ADP according to side rule. Here AO equals to AD equals to 6 units. AO equals to AD equals to 6 units. AP is the common side that belongs to both triangles, so AP equals to itself. AP equals to AP is a common side. And here we have also OP, that is equals to PD equals to 3 units. This is the radius of the semicircle. OP equals to PD equals to 3 units. Therefore, we proved that the two right triangles can relate to each other according to side rule, and from the fact that those two right triangles can relate to each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can relate to each other, therefore those two corresponding angles will be equal to each other. That is to say, angle OAP equals to angle PAD. And if we define angle PAD, PAO is theta, then from this equation theta equals to angle OAP equals to angle PAD, we derive that angle PAD is also equals to theta. This angle is also equals to theta. So we can find out that those two angles are both equal to theta. And then we focus on the right triangle AOP. The right triangle AOP, triangle theta equals to OP over AO. In the right triangle OAP, triangle theta equals to OP over AO. OP equals to 3 units, AO equals to 6 units, according to what is given us in the question. So in conclusion, we found out that triangle theta equals to 3 over 6. That is to say, triangle theta equals to 1/2. Okay, triangle theta equals to 1/2. Then we join points O and C together by a straight line. So we created triangle AOC. Then I presented to you the law of cosines, and we implemented the law of cosines in this triangle AOC. So what is the law of cosines that I already mentioned in the previous lecture? Here we have triangle ABC, that could be any triangle. Side AB of triangle ABC equals to A units, side AC equals to B units in itself, and side BC equals to C units in itself. Then according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times AB times cosine theta. Okay? So we implemented the law of cosines in triangle AOC, so I copied triangle AOC from the original drawing. We know that angle OAC equals to 2 theta, AO equals to 6 units, it is given us in the question. AC is the line segment that we are looking for, that is equal to x, and OC is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point O, and ends at point C, that is a point on the quarter circle itself. Here, point O is the center of the quarter circle, and point C is the point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle, that is equal to 6 units. Okay, so here we implemented the law of cosines on this triangle AOC. In this triangle AOC, we get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay? Again, OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. OC equals to 6, so OC squared is 6 squared, it is 36. AO is also 6, so AO squared is 6 squared, it is also 36. And it is plus AC squared. AC equals to x, so AC squared is x squared, minus 2 times AO, that is 6, times AC, that is x, times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. And what is left from equation number 1 after we cancel 36? On this side of equation number 1, we have 0. And the other side of equation number 1, we have x squared Minus 2 times 6 is minus 12, so this expression equals to minus 12x times cosine 2 theta. So in conclusion, according to equation number 1, we found out that 0 equals to x squared minus 12x times cosine 2 theta. We added 12x cosine 2 theta to this equation, equation number 1, and we found out that 12x cosine 2 theta equals to x squared. We divided this equation, equation number 1 by x, and we found out that twelve cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of x is to find out the value of cosine 2 theta. And we have trigonometric identity for cosine 2 theta. According to the trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. And we have already found out that tangent theta equals to 1/2. So we can substitute tangent theta in this trigonometric identity by 1/2. We did it, and we got that cosine 2 theta according to this trigonometric identity equals to 1 minus tangent square theta. Tangent theta equals to 1/2. So if tangent theta equals to 1/2, it means that tangent square theta will be equal to 1/2 squared. So tangent square theta equals to 1/2 squared over 1 plus tangent square theta, that is 1/2 squared. 1/2 squared is 1/4. So if cosine 2 theta equals to 1 minus 1/2 squared, that is 1/4, over 1 plus 1/2 squared, that is 1/4. So here cosine 2 theta equals to 1 minus 1/4, that is 3/4, over 1 plus 1/4, that is 5/4. So in conclusion, we have 3 cosine 2 theta equals to 3/4 over 5/4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with cosine 2 theta that is equal to 3/5. We found out that cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in this equation, equation number 1, by 3/5. So I copied equation number 1 here. 12 cosine 2 theta equals to x. And we substituted cosine 2 theta by 3/5. And we got that here, according to equation number 1, 12 times cosine 2 theta, that is 3/5, equals to x. That is to say 12 times 3 is 36. And 36 over 5 equals to x. So we found out that x equals to 36 over 5. And 36 over 5 is 7.2 units. So in conclusion, we found out that the length of line segment x, that is actually also equals to AC. Here, x, that is equals to AC. AC equals to x, it is equal to 7.2 units. We finished with the first method. Then I presented to you how to find out the length of line segment AC, that is equal to x, according to the second method. In the second method, we used all the things that we have already found out in the first method. The center of the semicircle is point P. This point, the point of tangency of tangent AC with this semicircle is defined as point D. We have only found out that OP equals to 3 units, PB also equals to 3 units, and PD equals to 3 units. It is the radii of the semicircle. And here we join points A and P together by a straight line. And we have only found out that those two right triangles can go into each other according to side rule. Okay, triangle AOP can go into triangle APD according to side rule. And from the fact that those two right triangles can go into each other, we derive that angle OAP equals to angle PAD equals to theta. So if angle OAP equals to theta, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD equals to theta. This angle equals to theta. So both angles are equal to theta. All those things we already done in the first method. And here we did in the second method another construction. We actually extended line segment AD by straight line, and we extended line segment OB by straight line until they intersect with each other at point E. Again, point E is the intersection point of the extended line segment AC and the extended line segment OB. So here we created the right triangle, triangle AOE. In this right triangle AOE, AP is angle bisector because of the fact that it divides angle OAE into two halves. The first half is theta and the second half is also theta. Okay, so I go with the right triangle, triangle AOE in a new page, and we implemented the angle bisector theorem in this right triangle AOE. But what is angle bisector theorem? Angle bisector theorem is that the angle bisector, in this case we have triangle ABC that could be any triangle, and AD is angle bisector, line segment AD is angle bisector. Why? Because it divides angle BAC into two halves. Each half equals to theta. So the angle bisector AD, according to angle bisector theorem, divides the side that it eats. Angle bisector AD eats side BC, and it divides it into two parts. The first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. Okay? So that ratio, that is BD over DC, equals to the ratio between the angle's legs. We are talking about the angle that has been bisected into two halves, that is actually angle BAC, and the legs of angle BAC are BA and AC, and the ratio between those two legs is AB over AC. So that ratio, that is AB over AC, equals to the ratio that angle bisector AD divides side BC, and this is equal to BD over DC. So the ratio that angle bisector AD divides side BC, that is actually BD over DC, equals to the ratio of the angle's legs, that is actually AB over AC. In conclusion, AB over AC equals to BD over DC. So the ratio that angle bisector AD divides side BC, that is BD over DC, equals to the ratio of the angle's legs, and the ratio of the angle's legs is AB over AC, and this is equal to the ratio that angle bisector AD divides side BC, that is actually BD over DC. In conclusion, AB over AC equals to BD over DC. Okay, so we can implement the angle bisector theorem in our drawing in triangle AOE, because we have AP, that is angle bisector, so angle OAE divides line segment AP divides angle OAE into two halves. Each half equals to theta. So I copy the right triangle AOE in this new page. You have here angle bisector AP that divides angle OAE into two halves. Therefore, according to angle bisector theorem, the ratio that angle bisector AP divides side OE is OP over PE, and that ratio equals to the ratio of the angle's legs, or between the angle's legs. And the ratio between the angle's legs is OA over AE. So the ratio between the angles legs is the OA over AE, and it is equal to the ratio that angle bisector AP divides side OE, that's actually OP over PE. In conclusion, according to equation number 1, AO over AE equals to OP over PE, according to angle bisector theorem. Okay, so here AO equals to 6 units, AE is AE, OP equals to 3 units. This is the radius of the semicircle. And PE is PE. So in conclusion, we found out that according to equation number 1, 6 over AE equals to 3 over PE. Here we divided equation number 1 by 3 and we multiplied it by PE, and we found out that according to equation number 1, 6 over 3 equals to AE over PE. 6 over 3 is 2. So in conclusion, according to equation number 1, we found out that 2 equals to AE over PE. We multiplied the equation number 1 by PE and found out that 2 times PE equals to AE. So AE is twice as long as PE. We defined PE as A. Here PE equals to A. Here PA equals to A according to our definition. And according to equation number 1, 2 times PE equals to AE. So 2 times PE is A. That is to say, A equals to 2 times PE, that is 8. A equals to 2A. So we found out that A equals to 2A, and P equals to A according to our definition. Then we implemented the Pythagoras theorem on the same right triangle, triangle AOE. So I copied the right triangle, triangle AOE in a new page. As you can see here, side OA, side OE, this side equals to 3 plus A. Okay. Here, I copied the right triangle AOE in this new page, and we already found out that OE equals to 3 plus A, AO equals to 6 units according to what is given us in the question, and we have already found out that AE equals to 2A. The hypotenuse A equals to 2A, this angle is a right angle, therefore this is a right triangle, so we can implement the Pythagoras theorem on the right triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is AE, so the square of the hypotenuse is AE square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AO square plus OE square. So A equals to 2A, so AE square will be equal to 2A square. That is equal to AO square. AO equals to 6, so AO square is 6 squared, that is 36. Plus OE square. OE equals to 3 plus A, so OE square will be equal to 3 plus A square. Here we open the brackets on both sides of equation number 2. So 2A squared is 4A squared. That is equal to 36 plus 3 plus A squared. 3 plus A squared equals to 3 squared, that is 9 plus A squared plus 6A. Here 36 plus 9 is 45. So 4A squared equals to 45 plus A squared plus 6A. We subtracted A squared from this equation, equation number 2, and found out that 4A squared minus A squared is 3A squared. Here A squared minus A squared is 0. So in conclusion, we found out that 3A squared equals to 45 plus 6A. We divided this equation, equation number 2 by 3, and found out that 3A squared over 3 is A squared, 45 over 3 is 15, and 6A over 2, or 6A over 3 equals to 2A. So in conclusion, we found out that according to equation number 2, A squared equals to 15 plus 2A. We subtracted 15 and also 2A from this equation, equation number 2, and we got the quadratic equation that A squared minus 2A minus 15 equals to 0. So in this quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 2, and the coefficient c equals to minus 3. And the general formula for a quadratic equation, the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. The variable that we are looking for in our specific quadratic equation is a, so x equals to a. So here we put the data inside the formula for x, and found out that x that is equal to a equals to minus b, b equals to minus 2. So minus b is minus 2, that is plus 2, plus minus square root of b squared. B equals to minus 2, so b squared is minus 2 squared, that is 4. Minus 4 times a is 1, times c, that is minus 15. Over 2a, a is 1, so 2 times 1 is 2. So here we found out that a equals to 2 plus minus, minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root we left only with 64. So in conclusion, we found out that a equals to 2 plus minus square root of 64 over 2. The square root of 64 is 8. So in conclusion, we found out that a equals to 2 plus minus 8 over 2. So here we will have two solutions that are possible for a. The first solution is a1 equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. But here, because of the fact that that a is the length of side PE, it must be a positive number. So a is a length, and as a length it must be a positive number. It can never be equal to minus 3, that is a negative number. So we cancel this solution. This is incorrect solution, and we left only the second solution, that is actually a equals to 2 plus 8 over 2 2 plus 8 is 10, and 10 over 2 is 5. So I found out that a equals to 5, and here, what is the length of BE? BE, for the moment, it is very easy to see that BE equals to PE minus PB. Again, BE equals to PE minus PB. PE equals to 5 units. PB equals to 3 units. So in conclusion, B equals to 5 minus 3, that is 2. Here B equals to 2 units. And what is the length of line segment CE? From the drawing, it is very easy to see that CE equals to AE. Here CE equals to AE minus AC. Again, AE minus AC equals to CE. Okay? CE equals to AE minus AC. AE equals to 10 units. Here, A is 2A and A equals to 5, so 2A equals to 10, so AE that is equals to 2A equals to 10 units. A equals to 10 units, and AC is the variable that we are looking for, that is X. AC equals to X, according to what is given us in the question. So in conclusion, we found out that C equals to 10 minus X. So we can write here that C equals to 10 minus X. Then I presented to you a new rule that is actually rule number 3. And we implemented rule number 3 in our drawing. What is rule number 3? According to rule number 3, if two chords intersect with each other outside the circle, so they intersect with each other externally at point P. Point P is the intersection point of the two chords with each other. Then the following equation is true. That is actually PA times PB equals to PC times PD. Okay, so we have here chord AB and chord CD that intersect with each other outside the circle, that is at point P. Point P is the intersection point between those two chords. So if this is the reality, that we have two chords that intersect with each other outside the circle at point P, then the following equation is true, that PA times PB equals to PC times PD. So we can implement rule number 3 in our drawing. Why? Because in our drawing we have, but before that we actually completed the quarter circle to a circle, and we extended line segment BO by straight line until it touches circle at this point, point M. Point M is the touching point of the extended line segment BO and the circle. So what is the length of line segment OM? O is the center of the quarter circle and also the center of the circle itself. M is the point of the circle itself, and this is exactly the definition of a radius. So OM is the radius of the quarter circle, that is to say, that is also the radius of the circle, that is to say it is equal to 6 units. Okay? So here we have chord MB that intersects with chord AC at point E. Point E is the intersection point of those two chords, and so therefore, because of the fact that the two chords intersect with each other outside the circle at point E, then we can implement rule number 3 in our drawing. I'll repeat again. Chord MB intersects with chord AC at point E, therefore, according to rule number 3, we will get that here EC times EA, again EC times EA, equals to EB times EM. Okay, EC times EA equals to EB times EM, according to rule number 3. EC equals to 10 minus X, EA equals to 10, EB equals to 2, and EM equals to 6 plus 3 that is 12, 12 plus 2 is 14. So in conclusion, we found out that 10 minus X times 10 equals to 2 times 14, that is 28, or 10 times 10 minus X equals to 28. We divided this equation by 10, and we found out that 10 times 10 minus X over 10 is 10 minus X, and 28 over 10 is 2.8. Here we added X to this equation and we subtracted 2.8, and found out that here X equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we found out that X, this line segment X, equals to 7.2 units in both methods. Okay, so the answer to the question that X that is equal to AC, it is equal to 7.2 units. Okay, thank you very much.